In this video, we'll finish up a problem that we started in the lecture, namely example 1, which is to find the antiderivative of 1 over x squared minus 5x plus 6. We decided to do this the hard way using trigonometric substitution. For that, we had to start off with completing the square and then using a substitution u equals x minus 5 over 2. That simplified our integral to the integral of 1 over u squared minus 1/2 squared du. We then used trigonometric substitution with the substitution u equals 1/2 secant theta, and that led to the following right triangle, where we saw that tangent is equal to 2 times square root of u squared minus 1/2 squared over 1. We then used all of that to convert this u integral into a theta integral. And after some simplification, we found that the integral simplified to 2 times the antiderivative of cosecant theta d theta. And then we could use rule 13 to simplify that integral to negative 2 ln of the absolute value of cosecant theta plus cotangent theta plus a constant c. We can then use the information from the right triangle to convert cosecant theta to 2u over 2 times square root of u squared minus 1/4, and we can convert the cotangent using the right triangle to 1 over 2 times square root of u squared minus 1/4. So that's what is being done down here. And in the interest of time, I just wrote out all the subsequent steps. These are not steps that you will have to do when you're taking the exam. This is just to show how complicated trigonometric substitution can be. So we plug in the values of cosecant theta and cotangent theta. Then you see that both of these terms have the same denominator, so we can combine the numerators. The 2u plus the 1 gives us the 2u plus 1 in the numerator, and then we keep the denominator. Now, what we also see is that there is a negative 2 on the outside and a division inside the logarithm. So the division by the rules of exponents becomes subtraction. So the numerator 2u plus 1 shows up in the first term, and the second term will be the 2 times square root of u squared minus 1/4 from the denominator. And meanwhile, we still have the negative 2 that's being multiplied by both of these terms. Now we see that the negative 2 is multiplied by a negative ln, so I pull that to the front so I can make that positive 2 ln times, or ln of the absolute value of 2 times square root of u squared minus 1/4, and then we have a minus 2 ln of the absolute value of 2u plus 1. Now, bringing in that factor in the front, we can use the rule that a ln p is ln of p to the power a. So for the first term, what we get is we get the 2 squared and then the square root squared. So that gets rid of the square root, and we're just left with u squared minus 1/4. And then for the second term, we do negative 2 times the ln of 2u plus 1. That becomes 2u plus 1 squared. And when you FOIL that out, you get the 4u squared plus 4u plus 1. Then we're going to use that u is x minus 5 over 2. And then after some algebraic manipulation, we can simplify the 4u squared minus 1/4 to 4x squared minus 20x plus 24. And then for the second term, this becomes 4x squared minus 16x plus 16. And then we still have the constant of integration. Now what you note is that on the inside of both natural logs, we can factor out a factor of 4. Now, if you take out that 4 in a multiplication by rules of logarithms, that becomes an addition. So we have ln of 4 plus ln of x squared minus 5x plus 6. And then for the second part, we have a minus ln of 4, and then a minus ln of x squared minus 4x plus 4. So, and that's actually incorrect here in the video. There's a minus there. In the end, we then get ln of x minus 2 plus ln of x minus 3, because we can factor the x squared minus 5x plus 6. And then for the second part, we can factor x squared minus 4x plus 4 as x minus 2 squared. And then with the negative in front, that becomes negative 2 ln of the absolute value of x minus 2 plus a constant. And so we can combine the ln of x minus 2 and the minus 2 ln of x minus 2, and the final answer is then ln of x minus 3 minus ln of the absolute value of x minus 2 plus a constant of integration. So what we can ask ourselves now is, can we find that answer a bit quicker? Because the x squared minus 5x plus 6, that actually factors into x minus 2 times x minus 3. So that seems too much of a coincidence that we got that answer. So we'll now find a faster way of finding the integral of 1 over x squared minus 5x plus 6. And what we have to note for this is that we can actually rewrite the integrand 1 over x squared minus 5x plus 6 as follows. So if you take 1 over x minus 3 and you subtract 1 over x minus 2, what do you get? Well, we'll have to find a common denominator. So we can multiply our first fraction by x minus 2 over x minus 2. So we'll get x minus 3 times x minus 2 in the denominator. And then for the second part, we multiply top and bottom by x minus 3. And so we end up with x minus 3 over x minus 2 times x minus 3. So now we have two terms that have a common denominator, and so we can combine these two fractions by keeping that common denominator. So the common denominator is x minus 3 times x minus 2. And we know that when you FOIL that out, you get x squared minus 5x plus 6. And then in the numerator, we get x minus 2 minus x minus 3. And that simplifies quite a bit because the x's cancel out, and then the negative 2 minus minus 3 gives us 1 in the denominator. So this is a way to rewrite the integrand. Now, you can ask yourself, like, how did you know that we had to subtract those two terms to get that 1? And you're right to ask that, because this kind of came out of thin air. So in the next video, I'll show you how to go from the right side to the left side. So if you start out with 1 over x squared minus 5x plus 6, how do you end up with those two fractions? But once you know this, we can actually rewrite our integral, the 1 over x squared minus 5x plus 6, as the antiderivative of 1 over x minus 3 and then minus 1 over x minus 2 dx. Now, because the integral of a difference is the difference of the integrals, we can break that down. We get the antiderivative of 1 over x minus 3 dx, and then minus the integral of 1 over x minus 2 dx. And by a simple u substitution, if you'd like, you could use the u substitution, u equals x minus 3. You see you end up with 1 over u du, and the antiderivative of 1 over u is ln of the absolute value of u. So the first integral is ln of the absolute value of x minus 3, and the second integral will give us the natural log of x, the absolute value of x minus 2. So that is the same answer, but a whole lot less work. So in the next video, we'll talk about how to find that decomposition of the fractions.